now busy with coating processes to meet the requirements of a high-end fashion with an eye to innovation and sustainability. She's going to present a study on the nickel release on stainless steel 316L, which is usually considered as safe. Yet, the electrode deposition process could cause an important nickel release. Her presentation is pointing out that the nickel release in the case of stainless steel 316L can be reduced using superficial treatments, maintaining the passivation state, especially when electrode deposition techniques are used for applications where nickel exposure is to be strictly controlled. Mrs. Roberta Emanuele. Good afternoon, ladies and gentlemen. Thank you for your kind invitation. Thank you very much to all of you for being here. I shall be talking about the process optimization for stainless steel 316 with an innovative approach. I'm going to provide you with some background information. Stainless steel is an alloy which is made of chromium and aluminum and iron. It could be recycled. Stainless steel is a specific type of steel, including 10.5% of the maximum of chromium. Actually, a minimum, says the speaker, of 10.5, a maximum, and the maximum is 1.2. Chromium oxide external state makes it resistant to corrosion. Thanks to this characteristic, this is a material which is widely used in many different industries. In the building sector, in the chemical industry, in the aerospace industry. To classify stainless steel is the American Steel Institute, and usually a 3-digit number refers to the strength, the most important alloying metals, and then there are references to other metals of the alloy that refer to the strength of the different type of steel. And then at the end, there's a letter adding information. L in this case stands for low carbon. AISI 316L is a specific type of stainless steel. It is a chromium nickel alloy containing 65% of iron, chromium ranging between 16 and 18, and nickel from 10 to 15%. This type of steel is also used for medical purposes. It is not widely coating because, again, the coating is very difficult in the case of this type of steel. The chromium oxide layer makes it resistant to corrosion, so much so that coating is very difficult. Usually, to coat this type of steel, nickel wood is used. This is a material that has many additional problems. Once in touch with this material, different percentages of men and women develop allergies. This is why it was banned by the European Union in the case of the nickel release being higher than 0.5 micron per centimeter over the week. This is the amount which may provoke an allergic reaction. There's a law regulating the use of this material. It is UNI EN 1811/2023. and the threshold levels are 0.2 micrograms per centimeter per square centimeter per week, with the highest level being a 0.5 microgram per square centimeters in the case of objects that are constantly in touch with the skin, i.e. necklaces and rings. Stainless steel 316L, in case of a saline environment, is subject to corrosion, but the steel 316L, Telkel, does not release any nickel compound. In case of it being coated and galvanized, it might be subject to release because in the case of 316L, there's some 12% of nickel. So once the chromium oxide layer is removed, the release is promoted. In this paper, we've analyzed the nickel release after different electrochemical stages from the preparation of the sample on, to understand how nickel is released and to find solutions to stop this release. The flow diagram can be summed up as here. So the samples were characterized by means of different technique. After the week of testing, the samples were rinsed and raised and were analyzed with the SEM microscope to look at the amount of nickel released, and the solution has been analyzed with an MPAES test. Let's have a look at the results of this release test. Based on the legislation, samples are to be cleaned with a solution, and then they should be suspended within a container where a solution of artificial sweat is included with sodium chloride 0.5%, 1.1% of urea, and 0.1 of lactic acid. The pH should be equal to 6.1 to 0.1, and the added solution should be proportional to the sample of the area. 1 square centimeter, 1 milliliter of the solution. So the samples are left within the solution for a week. At the end of the week, this solution is analyzed with MPAES to understand the quantity of nickel per square centimeters released over the week. We looked at the literature. This is a SEM test after the images that was taken after the test. We know that stainless steel 316L does not release nickel unless retreated. We look at the electrochemical cleaning. This is a process which is always resorted to for adequate coating. Usually it is performed for 60 seconds. And to look at the role of this electrochemical polishing, we looked at 3 potential solutions: 1, 20, and 100 for square decimeter. And with a sulfuric acid solution is used. 2 sets of samples have been identified. One was neutralized with a solution and one was not. But irrespective of the current being used, none of these samples yielded or released any nickel. As a matter of fact, there are no morphological, no composition variations after the test. So we may clearly say that the polishing, the degreasing process does not lead to any release. In the case of oxygen getting in touch, in that case, something might happen. We then looked at the role of the coating. As I said earlier on, the solution which is mostly used is the wood nickel bath, which is a galvanic bath with the chlorhydric acid and nickel chloride. It is extensively used and has been since the 50s, and it is still being used even after the adoption of the legislation. In my work, we've looked at the nickel-free solution, which was gold-based, that has been studied to have the deposition of a metal on the external layer. These two baths was compared to analyze the nickel release, and they enabled to understand what were the decisive factors and to see to what extent the coating, the galvanic process, as well as the surface treatment may have an impact on nickel release, as, for example, superficial roughness. The first part of this research has analyzed the roughness. We looked at the roughness of two different samples, one of a raw stainless steel 316L, and the other one had been treated. You see the difference between the two samples. One is much better polished than the other one. And the FM image is very representative. If you look at the data for SQ and the two data are very different. The first set of samples was prepared using as a substrate stainless steel 316L. We then looked at the performance of the wood nickel bath. The first set of samples have been submitted to this bath, depositing gold, 0.3 micron layer of gold at 24 carats. These are the SEM images of the samples before the release test, and these are the images after the test. As for the results, these are all average of 3 repetition, and as you see, the release tests are higher than allowed by the law. For the samples produced with the golden layer, the figure is halved. You might think that the nickel is released by the substrate of wooden nickel, and yet this is counterintuitive because nickel is only included in the substrate. So this means that the superficial activation and the removal of the chromium oxide that was necessary for the coating made it more liable to release nickel. In the SEM message, you see that there are many cracks on the surface, so probably nickel is released by these very cracks, where there is a problem with adhesion, and that could be due to an excessive roughness of the sample. We then use the other type of 316L steel that was polished, and you see that the results are quite clear. In the case of the samples that were subject to coating with wood nickel, we don't comply with the rule, whereas if we use gold, the results are much better. We can therefore say that superficial roughness of the sample bears importantly on the final result in terms of nickel release. We then performed additional studies using the polished stainless steel 316L and we've resorted to galvanic layering, which is used in the case of custom jewelry, that is copper, bronze, palladium. The samples were then tested. These are the images after the release test. And unexpectedly, the results were good for both sets of samples. There are very high results in terms of nickel release. In the other case, we have 1, 2, 5. In this SEM messages, there are cracks visible, as well as results of the corrosion. That white part is copper that is released by the layers underneath the substrate. The data we obtained on the samples with the final layer of gold gives us good result. 1.25 is the measurement of the gold layer. In the case of the samples galvanized with nickel, the results of the are similar. In the case of the gold layer, there's one sample that released less nickel complying with the law 0.025. And this increased the standard deviation, coming very close to the average value. Based on this study, we may say that had we assumed that there was a nickel dispersion in the intermetallic phase, was wrong, because the time since the preparation of the sample and after the week of release is not enough to enable nickel to get across the galvanic coating. The presence of this coating seems to further promote the release of nickel. And this is probably due to the fact that we introduce additional variables in terms of of the lattice tensions. We then prepared another set of samples following the same cycle as before, with the only exception being the final deposition of gold to get to the final thickness of 1 micron. So again, the samples were checked and the release tests were extremely good. Indeed, they both comply with the existing limits, so there's no variation detected with the SEM in terms of standard deviation. The thickness of gold, of course, bears importantly on the release of nickel. In the literature, we read that with layers less than 0.8, we have a great porosity. And you see the image of a sample that has been coated with a 0.8 micron of gold. And on the right-hand side, you see that pores are visible. And it is probable that from these pores, the nickel gets to the substrate. So a higher, thicker layer prevents this pore from occurring and prevents nickel from getting to the surface. The samples with 0.2 microns are very ruined. You see the copper deriving from corrosion that stain the sample. On the right-hand side, we see that the sample are much better. So porosity bears importantly on the release of nickel. But there is another factor to be considered, which is perhaps even more important, and that is the removal of chromium oxide. To further confirm this, another set of samples had been prepared using PVD technology, as physical vapor deposition. So we put gold on the steel without removing oxide, and we deposit only on one side, leaving one part non-covered. So we tested the samples, and all turned out to be within the limits as set by the legislation. So based on all the tests performed, we believed we have better understood how nickel release works. Stainless steel 316L doesn't lead to any release. Not even after the decreasing and polishing do we get any nickel release because there is something protecting the release. In the case of a metal being added and the previous removal of chromium, in that case you cannot have a second time passivation. Using thicker layers of gold, avoiding any porosity, we can prevent nickel from being released because there are no gateways for its coming out. Gold deposition by means of physical vapor deposition proved to play an important role. Roughness also bears importantly. Indeed, rougher surfaces are much more likely to release nickel as compared to polished samples. With the galvanic deposition, you may have different currents. In the case of more current, there's going to be a thicker layer. And in the case of high surface roughness, you're going to have a lot of potential corrosion. To conclude, stainless steel 316L and stainless steel as such is an extremely valuable material. Thanks to its chemical and physical properties, it could be recycled. Galvanic coating, when nickel-free processes are used, could all the same lead to nickel release. We have to have a polished surface with no roughness. We could use gold as a coating layer so as to reduce the release. The release indeed is being caused by the removal of the chromium level, which is necessary for the covering layer to be in closer connection with the underlying material. So basically, we succeeded in the limiting nickel release, understanding also how to better improve in the future. Should you be interested in carrying out further research, you can find a paper, our study, on this magazine. Thank you very much for your kind attention. Thank you very much for having me.
Ringrazio la dottoressa Emanuele.
Thank you very much, Mrs. Emanuele.